Page 5 of Chapter 6, Complex Numbers and Polynomials for HL. Um, so on page 179, there is yet another thing that Gauss did, which is he's the first one who did something useful with complex numbers. What he did was he demonstrated that it was not possible to trisect an angle with constructions. And in just like 100 years ago, or maybe 150 years ago, the first application of complex numbers by Steinmetz was that he used complex numbers to analyze electrical circuits. So if you are going to be any kind of engineer, you will definitely take a circuits class, and in the circuits class in college, you will analyze circuits with inductors and capacitors in it, which means that the you're going to push trig functions through it, and then you're going to have like phase changes due to inductors and capacitors, and because of that, you're going to use complex numbers to as kind of like a convenient shortcut notation to represent phase delayed trig functions, and we can talk about that in class if you'd like to. Complex conjugates. So if the complex number z is equal to a plus bi, we write its conjugate as z star equals a minus bi. On page 176, we saw that multiplying by the complex conjugate makes a complex denominator real. Real quadratics are quadratics with real coefficients, but not necessarily real roots. Okay. So real quadratics can have complex roots. If a real quadratic equation has discriminant less than 0 and c plus di is a complex root, then the complex conjugate c minus di is also a root. So if c plus di and c minus di are roots of a quadratic equation, then the quadratic equation is that for some constant a not equal to 0. And it says to prove it. Okay, so if we know that these are two roots of a quadratic, we know that those are the only two roots of the quadratic because the quadratic only has two roots. And we could write it in like factored form, right? So let's put a there to make it a general quadratic that doesn't necessarily have a leading coefficient of 1. So we'd have x minus c plus di times x minus c minus di. Okay, now we're going to FOIL. So a x squared minus c plus di minus c minus di and then I'm going to multiply the complex conjugates together, and I'm going to get c squared and let's see, let's do that real quick here. So c squared minus negative 1 d squared plus cdi minus cdi. So basically it's c squared plus d squared. Okay. Okay. And now let's simplify this. So we have minus c minus di x minus c plus di x. So these two can be added together, minus 2c x. These two subtract from each other, give 0. So that would be x squared minus 2cx plus c squared plus d squared, and that's it. We got exactly what they did, right? Okay, that wasn't so bad. Didn't even use all the space. Okay, example 7 and 8 on page 178. Find all quadratic equations with real coefficients and roots of 3 plus or minus I, 2 plus or minus square root of 3, etc. Okay, so let's look at the first one, 3 plus or minus I. In this case, so basically we can use this formula up here, and if C equals 3 and D equals 1, then we could say that the quadratic equations that have those solutions are A, x squared minus 2c, so it would be minus 6x plus c squared, which is plus 9, plus d squared, which is 1. So that would be a x squared minus 6x plus 10. Let's do E. E would be a x squared minus 2cx, so it would be minus 4x, plus c squared, so 4, plus d squared, so 3. So it would be a x squared minus 4x plus 7. Okay, let's do C. So it would be a x squared minus plus 4, because 2c would be negative 4, so it's minus 2c, which would be plus 4x, plus c squared, which is 4, plus d squared, which is 25. So that's x squared plus 4x plus 29. What about this one? It would be a x squared minus 2cx. There is no c, right? Because there's just an imaginary part for this one. Plus c squared, there's no c squared, plus d squared, which is going to be square root of 2 squared, which is 2. I just noticed I did something wrong on E. Did you notice that this is not square root of 3i, it's just square root of 3? So let's redo this, okay? So erase that, erase that. So minus 2cx, so it's going to be 4x, and then the last term is going to be 2 plus square root of 3 times 2 minus square root of 3 squared. So let's figure that out. So it's 4 minus 3. So the last term is going to be 1 instead of what I found before. I think I found like 3 or something. Okay? That was a little tricky because I thought that was I, but it's not. Number 2, find the exact values for a and b if 3 plus I is a root of this expression here, where a and b are real. Okay, so if we know that a and b are real, they're real coefficients. If a quadratic has real coefficients, we know that if there is a complex root, the complex conjugate is also a root. So we have 2 roots, 3 plus I and 3 minus I. And so now we know all the roots of the thing. Okay, so if we know that one of them is 3 plus I and the other one is 3 minus I, we could do one of the things. One is we could expand this, and then we would find this. The other way we could do it is we could use the formula we saw above. So we know that if we have two roots, 3 plus I and 3 minus I, we know that we could write it as x squared minus 2c, so 6x, plus c squared, which is 9, plus d squared, which is 1. So it's x squared minus 6x plus 10. So a is minus 6 and b is 10. Okay, C. A plus AI is a root of this quadratic where A and B are real. It says careful. Okay. So if A plus AI is a root and B is real and 4 of course is real, then we know that A minus AI is also a root. So we could kind of figure out what this function looks like if you find the formula x squared minus 2c plus c squared plus d squared. So it's x squared minus, 2ax plus 2a squared. So first of all, we notice that minus 2a is equal to positive 4, right? Positive 4. And the other thing we notice is 2a squared equals b. Okay. So first of all, we know that 4 is equal to negative 2a. So that means a is also equal to negative 2. And we know that b is equal to 2a squared. So that's 2 times negative 2 squared, which is equal to 8. So a is equal to negative 2 and b equals 8. The reason why it says careful there is because what we just did only works if we assume that a plus ai really is a complex number, and you're like, okay, how could it not be a complex number? It's got an I in it. Well, what if a was 0? If a is 0, then basically what we're saying is one of the roots of the polynomial is 0. If one of the roots of the polynomial is 0, that actually implies that b is also 0. Because like if one of the roots is 0, then it can be written in the form of x times x minus c. If you wanted to write that in terms of x times x minus c, b has to be 0, right? Or you could also say like, okay, if one of the roots is 0, then that means that the b term, alpha times beta, is equal to 0 because one of the roots is 0. So if one of the roots is 0, it doesn't matter what the other root is. The b value here, or the constant term, is going to be 0. So that's another possible solution. A equals 0, b equals 0. Okay? Because they never said that a plus ai is a non-zero number.